I have to wait 9 minutes before I can start. For those of you not from U of T, 2 o'clock means 2:10. Also for those of you from U of T. For a little bit while we wait for 10 after. Not really, no. No, I have one, but this isn't. It's a Larry V. Alaskan guitar. I have Alaskan, but this isn't it. I have Alaskan, but this isn't it. Okay. Come now, says the clock. The sail has found its wind, so I nod to my friends and we begin. Another evening show finds me, and I know all I need to do is just give in. And ooh, I'm carried away. And ooh, I'm carried away. What more could there be but people in a room singing unafraid the same tune? I close my tired eyes and take in what I hear, and all those times of trying disappear. And ooh, I'm carried away. And ooh, I'm carried away. From this point of view, staring out at you, every wish I've made comes true. Come now, says the clock, the sail has found its wind, so I nod to my friends and we begin. And ooh, I'm carried away. And ooh, I'm carried away. That's a start. 4 more minutes. I can cram in another 1 or 2. Well, I am just the messenger. I speak to every man, every woman, every child who lives upon this land. My face is often hidden, many do not wish to see, but when you're in the mirror, sometimes you look at me. I am in the songs of children and the stories old ones tell. I am in the preacher's heaven, I am in the sinner's hell. I am in the endless wires strung beside the highway strand. I am in the veiled shroud of night that darkens midnight land. I am torn by this darkness, the deafness of my peers, as I watch the words of ages pass away, and all my quiet whisperings fall dead upon their ears, like the sun falls dying at the end of day. I am there among the trash heaps where the homeless people dwell, foundation for the mansions the rich man buys and sells. I am words not to be spoken in the company of thieves. I am tears upon the face of the widow as she grieves. I am the gentle cradle of a woman's loving arms. I'm sunlight in the meadow on the stream behind the farm. I'm knowing that you've done right by all your fellow men. I am the path that leads you lost and takes you home again. I am torn by this darkness and the deafness of my peers, as I watch the words of ages pass away, and all my quiet whisperings fall dead upon their ears, like the sun falls dying at the end of day. You ready to start?
I'm going to be 2 minutes. Yes. I'm going to be 2 minutes.
And you ready to go?
Yes, I'm ready to go. But you planning to sing some more? Maybe you should.
I'm
But
trying
let
to
me first
sing
do my
one-
intro, sit down, and
Right.
then you sing.
You do your intro, and then I'll do one more.
Okay. Ladies and gentlemen, it is with bittersweet emotions that I welcome you to the last lecture of Rick Hehner's retirement lecture series, Out with a Howl. That is the last lecture, as far as I know, that Rick is giving as a UT regular faculty member. I'm hoping by no means the last talk that you will be giving here. As you all know, he's retiring from the Department of Computer Science after 43 years at the University of Toronto, first as a PhD student and then as a faculty member. Rick received his first degree in mathematics and physics from Carleton University in 1969, his PhD in computer science from University of Toronto in 1974, and then joined the faculty, becoming a full professor in 1983 and Bell University Chair in Software Engineering, now in this century, in 2001. His research has been mainly on the subject of formal programming methods and the mathematics of program construction in the areas of programming methodology and software engineering. He invented predicative programming, which is a method for program derivation and proof. And those of you who were here in the second talk saw the introduction to it. He has extended this work to the automated generation of proven circuits from programs, to probabilistic programming, and to quantum programming. Professor Hehner is the first winner of the annual Computer Science Undergraduate Teaching Awards and has been visiting scientist at Xerox Research Center in Palo Alto, visiting fellow at Oxford University, visiting researcher at the University of Texas, Austin, invited professor, I'm not going to try this in French, at Grenoble, visiting professor at UBC and University of Southampton. Rick has written 2 books and many journal and conference papers, has given appropriately 160 invited lectures at institutions around the world, taught short courses in Oktoberdorf in Germany, Macau in China, Turku in Finland, and Tandil in Argentina. He is a member of 2 IFIC working groups, 2.1 on algorithmic languages and calculi, and 2.3 on programming methodology. and an editor of Acta Informatica and of Journal of Formal Aspects of Computing. Rick Hehner graduated 12 PhD students, as far as I know, and 27 master's students, hosted 2 postdoctoral fellows, and taught thousands of undergraduates. Many of his former students I can see are in the audience today. Finally, before Rick gets to sing, again, let me announce that there will be coffee and cake upstairs on the 3rd floor of this building in 3248, right after this talk. So please join us for another chance to talk to Rick and have some cake. So, over to you.
All right. Thank you, Martha. Okay. Go. No general procedure for bug checks succeeds. I won't just assert that, I'll show where it leads. I'll prove that although you might work till you drop, you cannot tell if computation will stop. Imagine we have a procedure called P that for specified inputs permits you to see whether specified source code with all of its faults defines a routine that eventually halts. You feed in your program with suitable data, and P gets to work, and a little while later, infinite compute time correctly infers whether infinite looping behavior occurs. If there will be no looping, then P prints out good. That means work on this input will halt as it should. But if it detects an unstoppable loop, then P reports bad. That means you're in the soup. The truth is that P cannot possibly be, because if you wrote it and gave it to me, I could use it to set up a logical bind that would shatter your reason and scramble your mind. Here's the trick that I'll use, and it's simple to do. I'll define a procedure which I will call Q. It will use P's predictions of halting success to stir up a terrible logical mess. For specified programs, say A1 supplies, the first step of this program called Q I devise is to find out from P what's the right thing to say of the looping behavior of A run on A. So excuse me. If P's answer is bad, Q will suddenly stop, but otherwise Q will go back to the top and start off again, looping endlessly back till the universe dies and turns frozen and black. And this program called Q wouldn't stay on the shelf. I would ask it to forecast its run on itself. When it reads its own source code, just what will it do? What's the looping behavior of Q run on Q? If P warns of infinite loops, Q will quit, yet P is supposed to speak truly of it. And if Q's going to quit, then P should say good, which makes Q start to loop. P denied that it would. No matter how P might perform, Q will scoop it. Q uses P's output to make P look stupid. Whatever P says, it cannot predict Q. P is right when it's wrong, and it's false when it's true. I've created a paradox neat as can be, and simply by using your putative P, when you posited P, you stepped into a snare. Your assumption has led you right into my lair. So where can this argument possibly go? I don't have to tell you, I'm sure you must know. A reductio, there cannot possibly be a procedure that acts like the mythical P. You can never find general mechanical means for predicting the acts of computing machines. It's something that cannot be done, so we users must find our own bugs. Our computers are losers. So, this is the last of my farewell talks. And I put this particular talk last because I really think after you've heard it, you might not want to hear anything more from me. I already know that some of you, and maybe all of you, will disagree with what I'm going to say. But there's no point in telling me I'm wrong without telling me where I went wrong. You know, if you just say I'm wrong, well, you're just saying that I am disagreeing with the standard orthodox wisdom in computer science, and I already know that. If you think during this talk that you know where I go wrong, well, save it till the end and tell me then. I don't really want to debate it in the middle of the talk because then I will definitely get off track. Okay, so in just 11 days from now, June 23, Alan Turing celebrates his 100th birthday. Well, he may not celebrate it, but we'll celebrate it for him. Turns 100 in 11 days. And there's going to be a great big party for him in Manchester, England, and I'm going to be there. It's going to be great. There's going to be at least a dozen Turing Award-winning speakers there. Okay, so what I'm going to talk about here is a paper that Turing wrote 76 years ago when he was 24 years old. That's pretty good because that paper laid out most of the foundation, I think, of computer science. I mean, it defined what computing is, and it showed how to write a program which he called the universal machine, and we now call the universal Turing machine, but a program that can interpret any other program. So how to write an interpreter, which is standard today, but it was very groundbreaking then. And one of the things in that paper, in fact, on page 247 of that paper, is a proof that some particular program is incomputable. So we now call that the halting problem. It's only a page long in the paper, and this is the key paragraph in that, on that page. First thing I want you to notice about this proof is that, well, it's written in English, and it's very informal. And actually, it's a bit hard to read, too. I put some stuff in square brackets there to make it a little easier. That's the stuff in square brackets is mine. But you can notice at least that it starts off with an assumption of computability. Let us suppose that there is such a process. That's the assumption that the halting problem is computable. And then somewhere in the middle, we have what's called a diagonal definition. And in my square brackets, I said what happens when H works on the representation of H, which you can recognize from the song, is a key piece of the proof. The song was, by the way, a really good, accurate representation of this halting problem. So that's why I like it. And then finally, we come to a self-contradiction or an inconsistency. It says both verdicts are impossible, and we conclude there can be no such machine D. So the first thing I'm going to have to do in order to have a better look at this is formalize it. I'll start off by defining H to be the halting function. And whenever I say function in this talk, I mean a mathematical total function. I don't mean some programming language construct. I mean a mathematical function. And it's kind of standard to have two arguments. H tells whether execution of program number n terminates when started in state sigma. So if you want to pass a program as a parameter, you have to encode it as data somehow. And Turing encoded programs as numbers so that they could be arguments to functions. Well, actually, we do things slightly differently these days. Turing did not have the character string data type. I'll use the word text instead of character string. I just mean character string data type. And that is the way we pass programs around now. If you pass a program to an interpreter to be interpreted, you pass it as text, or to a compiler, you pass it as text. So let me change that to execution of program text P terminates when started in state sigma. Now, the next simplification I'm going to make is just to get rid of that second argument, sigma. It's easy. It doesn't help because I can just make the assumption that every program execution begins in the same state. It's kind of like initializing all variables to 0 to start with, which I'm not advocating. I'm just trying to simplify and get rid of a parameter here. Now, if that's not the state that you wanted to start with, well, just put some assignments at the beginning of your program to create the state that you did want. In other words, initial state creation becomes the initial part of the program. That just frees me from having to have a second parameter there. It's not going to change anything in the proof. And the final change, also quite standard these days, is instead of talking about Turing machine operations, I'm going to use a more modern programming language. So for example, H of the text representing assignment x gets 0 will be true because that's terminating execution. And H of text representing that infinite loop there while true do something is false because it's non-terminating behavior. Now we need the computability assumption. Assume that function H is computable and that a program, big H, has been written for it. Okay, well, if big H is supposed to be an implementation of the halting function, then when working on those same two examples, it should give those same two answers. It's supposed to be an implementation of the halting function. Well, next comes the diagonal definition. This is a formalization of the diagonal definition we just saw in Turing's paragraph there. So D is clearly defined as a text, and I will take all of those constructs there to be programming constructs. So it's a text representing a program. And so we can now ask, what do we get when we apply the halting program to this text? And the answer is, well, if H of D is true, don't know if it's true or false, but if it's true, then this program in here is equivalent to its then part. It is therefore an infinite loop. And therefore, H applied to it is false. If, on the other hand, H of D is false, then this program is equivalent to its else part, which is terminating, and therefore H applied to it is true. So, in other words, we have an inconsistency. Either way, something's wrong. And therefore, we conclude that the assumption we made must have been wrong. Function H is incomputable. There is no such program, big H. Okay, well, that's a formalization of the halting problem. I now intend to start criticizing it. And my first criticism is really mostly just a little warm-up exercise, not a serious criticism. But anyway, D is supposed to be is a text representing a program, we said. Okay, if, then, else, and while, and assignment, and let's say function application are all programming constructs. But for this to be a program, D has to be in the domain of H. D right here has to be in the domain of H if you want to apply H to it. Okay? Now, if D is in the domain of H, fine, we can apply H to it, and therefore this really is a program, and therefore this really is a text representing a program, and therefore D is in the domain of H, which is text representing programs. If, on the other hand, D is not in the domain of H, then we can't apply H to D. This isn't a program. This isn't a text representing a program, and so D is not in the domain of H. Well, I don't have an inconsistency here. I just have an inability to conclude or know that D is in the domain of H. I could make the assumption it is, that's fine. Then the argument can proceed, as I said it before. But then, when we come to the contradiction, maybe that's the assumption that's wrong, rather than the computability assumption. I mean, how do we know which assumption is wrong if we've made more than one? Okay, so I think that problem is fixable, and I'll show you a fix later. But I at least pointed out it was a problem with the argument that Turing gave. Now, the next thing is that you'll notice that I really just talked my way through the contradiction. I didn't actually formalize it, and I really should have formalized it. So I'm going to do that right now. H, when applied to D, well, just use the definition of D. There we go. H applied to that text. Now, how does H apply to a text representing an if program, or an if then else? Well, if H of D is true, this is the argument that we just gave. So if H of D is true, then that middle line is equivalent to H of the while loop. If, on the other hand, H of D is false, then that the program above it is equivalent to H of the assignment. And we know what both of those are because I gave them as examples. And now a little Boolean algebra allows us to simplify. And there we have the contradiction that I gave informally a few minutes ago. But now that it's formalized, I can see what's wrong with it. And what's wrong with it is that line called semantic transparency. That is, how does H apply to an if? I'll show it to you by just writing the same thing again, slightly differently. I'm going to start off with the definition of D. And now I'm going to apply H to both sides. Now that's just function transparency. It's if x equals y, then f of x equals f of y. That's a property of all mathematics, not just programs. And now I want to ask, how does H apply to a text containing an if-then-else? In other words, when is an if-then-else halting or terminating? And the answer is, well, first of all, the if part has to be terminating. All right. If the if part terminates with true, then the then part has to be terminating. If the if part terminates in false, then the else part has to be terminating. So I'll just say that. This says the if part has to be terminating, and if we get true, then the then part has to be terminating, else the else part has to be terminating. And now, yes, point to that. And now use the same examples for H of while and H of assignment, and use a little Boolean algebra. And I come to the line that we have on the bottom there, which says, first of all, that the if part is not terminating. And then it says, actually, and neither D is not terminating. Both of which I think are actually quite reasonable things to say, but there's no formal contradiction. We cannot get a contradiction out of this formally. We can argue informally why it's a contradiction, but there is no formal contradiction. Okay, well, I think I can fix this problem too, because I really want a formal proof of the halting problem, not just an informal argument. So I'll come back to that one later with what I think is a fix for that one too. So that the check mark means this is formally not an inconsistency. So here's what we've got for the halting problem. The next thing I want to tell you is that the halting problem has nothing whatsoever to do with halting. Not at all. And to convince you of that, I'm going to change it into the calumation problem. So little h of p tells us whether the execution of program text p calumates. You might wonder what that means. Well, I checked the dictionary to make sure that calumate is not in it. So it's just the word I made up. And I just picked two arbitrary examples, the first two that came to mind, and said H of this one, so this one is calumating, so H of this is true, and this one, let's say, isn't calumating, so H of this is false. Now, let's assume that this function is computable, the calumation function is computable, and that a program for it has been written. Since this is a program for calumation, therefore it has to give the same answers on the same arguments. Fine. Now we make a very similar sort of diagonal definition to the one we had before. And we wonder, what is h of d? And if h of d is true, then this if then else is equivalent to this assignment, which is not calumating. But if h of d is, if d is not calumating, h of d is false, then this is equivalent to x gets 0, which is calumating. So we have a contradiction. So we conclude that program H doesn't exist. Function H is not computable. And I don't even know what calumation is. But it's not computable. So that, to me, seems at least a little bit strange. In fact, so every function is apparently incomputable. Okay, let me get to the real heart of the problem. And in order to explain it better, I'm going to start off with something very familiar, Russell's barber. So in a small town, there are exactly 3 men named A, B, and C. A man named B is the barber, and the barber shaves the men in the town who do not shave themselves. Okay, not hard to formalize. For all men in the town, B shaves M, if and only if M does not shave himself. And we simply, is that called specialization? We specialize M to B, and in one short step, we have a contradiction. Well, this is all well known. I mean, everybody knows that Russell's barber comes to this contradiction, and therefore people call it a paradox. Why actually do they call it a paradox? I mean, why doesn't everybody just say, yeah, obviously, so you said something wrong, and that's the result? I think the reason is because the statement, the barber shaves the men in the town who do not shave themselves, seems reasonable. That's what barbers do. They shave the people, or the men who don't shave themselves. That's what barbers do. And the reason it sounds reasonable is that, well, what you're probably thinking shaves the other men in the town, you know. And of course, if I formalize it that way, for all M and the other men in the town, there is no such contradiction, and we haven't said whether the barber shaves himself, and we could say it either way, the barber does or doesn't shave himself, whichever we want, without inconsistency or without contradiction. Okay? I mean, we do this in English all the time. Somebody says, anybody there? And you say, nope, there's nobody here. Well, obviously, there's nobody here but me. You know, we're reasonable about these things. Okay, so now I'm going to ask a silly question. Is shaves computable? Okay, we define shaves such that the barber shaves the men in the town do not shave themselves. I'm defining it informally, and reasonable people say, yeah. And now we make an assumption that shaves is computable and that a program has been written for it. And then we suddenly discover an inconsistency, and then we conclude, nope, shaves couldn't possibly exist. Function shaves is not computable. Okay? Now, that's what happens if you start off with an informal definition. You don't notice the inconsistency until after you've made a computability assumption. All right? Is that possibly what might be happening with the halting problem? So I want to explore that for a few minutes. And so one way to explore it is just to remove the computability assumption. And the way to do that was very nicely given to us by Turing in his PhD thesis, where he invented oracles for the purpose of studying comparative computability. I was hoping for confirmation from Al back there, but instead I got a yawn. Anyway, an oracle, what's that? Well, it's something that we don't worry about whether it's computable, how it computes something. It just gives us answers, by magic if you like, it doesn't matter. And so that we can include it in a program. So let funny h be an oracle for the halting function. Well, then it's supposed to give the right answers for that assignment in that infinite loop. And then make a diagonal definition. Well, now I'm going to use that oracle in the diagonal definition. So my programming language has now been augmented by one oracle, which I don't assume is computable. But it does allow me to make a diagonal definition since it's been augmented by that. So h is in the programming language, and therefore I come to the same contradiction. You know, if h of d is true, then it has to be false. If it's false, it has to be true. Same sort of contradiction. So what should I conclude now? I didn't assume computability. There was no such assumption. Well, maybe you don't like oracles and worry, you know. If I introduce magic, anything can happen. Actually, what I'm saying is that even if we're given the values that we want for halting on any, within a program, even if we're magically given them, we still end up with the contradiction. That's all I'm saying. But in case you don't like oracles, I'll do it another way without oracles, because the modern way to talk about something that, even within programming language notations, for which you don't have an implementation, don't even know if it's computable, is just to talk about a specification. So I could let h of s this time be telling us whether text s represents a specification of terminating behavior. And so h applied to this is true as usual, applied to this is false as usual. And I can make a diagonal definition out of it, the same usual diagonal definition, and come to the very same inconsistency. And I haven't made any computability assumption to withdraw. So what should I be concluding? Well, when you come to an inconsistency, you have definitely got inconsistent axioms or definitions, I could say, because a definition is just an axiom. There's an inconsistency between little h and little d right there. You can't say where the fault lies. It's in the collection of things that give you the inconsistency. I could change the definition of little h and so that h and d are now consistent, or I could change or withdraw the definition of little d in order to preserve consistency. That would be fine too. If I'm going to withdraw the diagonal definition to preserve consistency of the halting function, then it isn't fair to ask the halting program to apply to that diagonal element. If I don't withdraw the diagonal definition and I have an inconsistency just with the definition or specification of halting function and some diagonal element, well, then it doesn't make any sense to even ask if it's computable. I've got an inconsistency already. Okay. You might worry, though, that this isn't the same D I had before. I mean, after all, I'm talking about specifications now. Well, I really only need a domain that consists of three things. This assignment, this while loop, same as before, and one diagonal element. Really just those three things. You know, if I reduce it to 2, I've got no problem. If I keep all 3, then there's no point in going on and checking into computability. But this little d, you might worry, is somehow different. So let me argue why that there is no difference and it doesn't matter. I'm going to do that with something I'm calling the mimic halting problem. So as before, h of s tells us whether text s represents terminating behavior or not. Now, I'm inventing mimic functions. So some functions might have mimic functions corresponding to them. Other functions might not have mimic functions. But if a function does have a mimic function corresponding to it, then the mimic function has to give the same results on the same domain elements. That's why I'm calling it a mimic. So I'm going to assume that function h has a mimic function big H. Not program here, I'm just talking about functions. But since it's a mimic function, then it has to give the same answers on the same examples. And now I can make a diagonal definition, same as before, come to a contradiction, same as before. And conclude what? Well, I assumed it was a mimic function, there was a mimic function, so I guess I should conclude that the mimic function doesn't exist. This is one of those functions that's not mimicable. Well, I see a few furrowed brows, and I'm glad, because what is this mimic function anyway? If applied to the same domain elements, you get the same answers. It is the same function. I mean, mimic was really dumb. But I show the structure of the argument is exactly the same structure of the argument. Now, I'm claiming this is relevant, but I'm not claiming that programs are exactly the same thing as mathematical functions. They're not. I mean, a program specifies a physical process, and it takes resources to compute, especially time, whereas a mathematical function is unconcerned with process and with time. It's just a mapping from a domain to a range. Okay? So I'm not claiming they're the same thing. But the halting problem, or the proof that we gave, makes absolutely no use of the computational nature of the program. It didn't talk about how it got computed or what resources got consumed while computing it. All it did is talk about what the answer is when applied to various domain elements. In other words, it was treating the halting program just as if it were a total mathematical function. All we're saying is applied to this, it gives that. Applied to something else, it gives something else. Okay? So in fact, all of these guys, the function we start with, the oracle, and the program that we're supposing, they're all mimics. Well, I won't say the program is a mimic. I'll just say all we've used about the program, the only knowledge about that program we've used is mimic knowledge. So we've treated it as if it is a mimic of the halting function. So whatever we end up saying about the halting program, we are saying that also about the halting function. And since H, well, all these three H's are all being treated as exactly the same thing, total mathematical functions from the same domain to the same range, then, therefore, these three diagonal definitions are actually all the same diagonal definition. It doesn't matter that one time I said I was talking about specifications and another time about programs. They are all the same, given that these functions are all used the same way. Okay, let me now simplify the whole thing as simple as I can. Maybe too simple, I'm not sure. But at least the structure of the argument will be the same. Let's suppose I've got a function little h from the naturals to the Booleans this time, and h of 0 is true and h of 1 is false. Now I'm not going to tell you anything more about little h. It might be the halting function defined as Turing defines it, applying to programs encoded as numbers. So that program number 0 is halting and program number 1 is not halting. Or maybe it's just the even function is telling me that 0 is even and 1 isn't even. Could be any function that at least satisfies these two equations. All right. Assume it's computable, that a program's been written for it, and therefore the program gives the very same results. Make a diagonal definition. Well, if h of d is true, then this is equal to 1, and therefore then d is equal to 1, and therefore h of d is false. But if h of d is false, then d is equal to 0, and h of d is therefore true. you have a question.
Yes, a clarification question. Is D a number or a function?
D here is a number. I mean, I've used the old version of algol, if then else, where the then and else parts are numbers here, but it's a number.
No, okay.
Yeah. Well, this is an expression that is attempting to define a number. I put the word attempt in there because we've come to an inconsistency. So something is clearly wrong. We can't define H this way, and D this way. We got to give up something. But in any case, the argument has exactly the same structure as the original halting problem argument. And therefore, if I were to use the same sort of conclusion, I'd be concluding that program big H does not exist, function little h is not computable, so the even function isn't computable, apparently. Okay. If I don't want to go past or don't want to make a computability assumption, I could have made the diagonal definition before making the computability assumption and come to the very same inconsistency. Okay? So that the computability assumption had nothing to do with it. So now, let me try a proof that solves as many of these problems as I can possibly solve. So, h of p is the halting function. Execution of program text p terminates. So, same as usual. Same two examples. Now, I'm not going to make a computability assumption. Why not? Because there's always some doubt. When you come to an inconsistency, there's some doubt as to which assumption is the cause, or what collection of assumptions are the cause, and what you should withdraw. And in fact, there are usually different ways to withdraw things to come back to consistency. So I'm not going to make a computability assumption. Let P be any program at all, not necessarily having any relationship with H. And it's from all texts to Booleans, not just texts representing programs. And the reason I've said that last part is now I don't have to wonder if D is in the domain of P. D is clearly a text. I don't even have to argue that it's a text representing a program. All I need is that it's a text. Now I can apply P to it. Therefore, this is a program. Therefore, in fact, D is a text representing a program. The strange thing to me is that D is the only thing I want to apply P to, and it is a text representing a program, but in order to be sure of that, I had to make it be a function that goes from all texts to Booleans, not just programs. Okay, so that takes care of that little problem that I raised earlier. Now there was another problem I raised earlier, and I started for that one with the definition of D, and I used function transparency to, this time I'm going to apply little h, the halting function itself. The halting function itself, not a program, is being applied to both these, to both sides. And now how does the halting function apply to this? Well, that we know by interpretation. This if then else is halting means, first of all, that the if part is halting. And if we get true, so if we get true evaluating it, then the then part has to be halting, and otherwise the else part has to be halting. And now we use our examples for little h to simplify and come to something that looks a lot like what we had before, but I never made any computability assumption here. So what I've got in this last line says the following. Now, I don't know whether h of d is going to be true or false. Maybe it's true. Let's say true for the moment. Well, then that says that the if part is halting. Yes. And it says that P applied to D is false. Well, that means that P cannot be an implementation of halting because h of D is true, and if h of D is true, under the assumption that h of D is true, P of D has to be false. So it can't be an implementation of the halting function. If, on the other hand, h of d has value false, well then, either the if part is non-terminating, doesn't halt, in which case, again, p cannot be an implementation of the halting function because it's supposed to terminate if it's going to be an implementation of the halting function. Or it gives the value true, which is the wrong value if h gives the value false. So what I'm concluding here is p cannot possibly be an implementation of the halting function, and p is any program. So isn't that a nice proof of the incomputability of the halting function? Well, it solves some of the problems I talked about, but not the main one. Suppose I'm in a programming language that includes a halting oracle. Okay? P could be that halting oracle. It's any program in the language. And this says, therefore, the halting oracle is not an implementation of the halting function. Well, of course it is. That's its definition. And if you don't like oracles, then I can talk about specifications instead. So, and come to exactly the same conclusion. By the way, is an interesting thing that I might point out right here. All these proofs are always non-constructive. So here it says, I don't know whether h of d is true or false, but either way, p is not an implementation of h. And the original one was using a proof by contradiction, which again is not constructive, but never mind all that. Here's a totally different way of looking at the proof of incomputability, the halting function. I'm going to look at self-duplicating programs. Some people call them Quine programs or self-replicating programs. I'm going to characterize a call in a program like this, sort of. What computation are you calling, please? The one named P. So this is call P within a program. Okay, fine, but there's another way to say what computation you want, and it's more direct. It goes like this. What computation are you calling, please? This one, right here. Okay, so instead of a call, I can directly say what computation I want. Now, if I'm using a call, P could be the computation in which this call occurs. In other words, it's a recursive computation. Down here with the direct method, how can the direct method possibly be the computation in which this occurs? Well, the answer is like this. Let OQ be the opening quotation mark. In any programming language, there's some way to say what the opening quotation mark is. Maybe you use a backslash, or maybe your programming language duplicates it, or I don't know or care, but some way of saying what the opening quotation mark and the closing quotation mark are. I need some program whose execution terminates and some program whose execution does not terminate. And now this is the computability assumption right here. Let's suppose that big H of P is a program that implements the halting function. And here is the diagonal definition, D. It's just a concatenation of texts, okay? It's a concatenation of these texts. I don't have time to go through the explanation. What I do have time to do is to say this is what we want to apply D to. It's a little hard to see what the arguments are, so I've underlined them. There are the three arguments for D. And the reason for applying D to that is what we get is something that has that exact same expression within it. So that you can have directly refer to a computation from within that same computation. Okay, so this is the program that I have just above there. You should, at your leisure, not right now, go through and show that, in fact, if you do apply D to these three arguments, you do, in fact, get this. So that program that it's on this line right here, the program, has this sort of form. if H applied to something, something, then N else T. That's what this is. If H applied to something, then N else T. Where this program is in fact, where P is in fact the whole program that I'm talking about. Okay? And now you can do the same, okay, this shows that the same thing is true. If I, back to this. I can do the inconsistency argument exactly the same way as before and come to an inconsistency. Or I can instead leave out that and just go back to the, use the halting function instead with specifications rather than, oh, I know what I was supposed to say one back. If the programming language contains the oracle, then as usual, we've shown that the oracle cannot be an implementation, the oracle for the halting function cannot be an implementation of the halting function, same as before. So that's wrong. Or if you don't like oracles, I could say the same thing about specifications. So I think that's rather a neat form of the argument, but the main criticism applies also to this, as it does to the original. Okay, so my conclusion, just on time. Well, Turing wanted to ask what functions are computable. And he really wanted to show a particular function that isn't computable. More often today, we would be asking the reverse question. We'd say, which programs have terminating executions? In other words, which programs are implementations of total mathematical functions? It's the same question in reverse. Okay, which programs have terminating executions? It seemed really important that programs have terminating executions back when we didn't have interaction with the execution of a program. Because if execution doesn't terminate, you've got no output, you've got no answer. But now, programs generally are interactive. And in fact, their execution terminates when you click on quit. That's when you get termination. And potentially, each program is non-terminating. If you want to sit there forever interacting with it, it will sit there forever interacting with you. So we don't have the same emphasis now, or shouldn't have the same emphasis now. Well, the pieces in between the interactions, they should be terminating, shouldn't they? Well, terminating is just nowhere near good enough. They should terminate within the bounds, the time bound of my patience, right? So termination isn't anywhere near good enough. What I really need is a nice small time bound on their executions. So all I'm trying to say right now is I think we got off to a bad start in computer science with an undue emphasis on termination all over the place. Okay, the main conclusion from this talk I want to give is that there is no proof that a well-defined halting function is incomputable. By well-defined halting function, I mean not a halting function together with a diagonal definition such that the two of them, such that we have an inconsistency. I mean, don't make that diagonal definition if you want a well-defined halting function. And then, when you implement it, it doesn't have to apply. The implementation doesn't have to apply to the diagonal element. So you don't come to an inconsistency there. Okay, and also all those other functions whose incomputability has been proven by reduction to the halting function, either directly or indirectly through a chain of other things, but ultimately to the halting function. So all those functions, we have no proof that they are incomputable either. I'm just waiting for tomatoes or darts or something to be thrown at me right here. Okay, well, I guess that's my conclusion, and that's the end of my talk. I'm open for questions. All right.